hear me? All right, it's 12, good afternoon. I'm Jayapaul from Pure Storage. So I'm going to look at AI from a different perspective. So the perspective that we work in office. So disclaimer, I don't want to blame any AI for any of my slides or my company. So it's all mine, or at least. All right, so this is a slide that you might be very familiar. You know, how many of you haven't interacted with an AI from morning? All of us are now used to talking to ChatGPT or to Gemini or some other software, right? You don't start your day without talking to one. So this part, I mean, we do a lot of things, and one of the things that we did recently is about the KV cache. So let me talk about it. Let me walk you through that. What it is about is, you know, if you look at an inference engine, it has two phases, prefill phase and decode phase. So there's a lot of things that is going on when you question. Let's say you ask about how's the, you know, where is this place located, for example. That's one of the common questions. Or let's say, can you tell me what this word is about? Or these days we are using it for our regional languages. Let's say your kids want to do some homework at home, they ask the question to an AI, right? So when you ask a question, what happens? The prefill stage kicks in, and it tries to break down. I mean, your query is broken down into tokens, and the tokens into embeddings. Embeddings is basically a vector, and then it is turned into a numerical form, right? After that, it goes to something called as a transformer block, where there is multiple layers. It looks at different heads, different perspectives. One from a syntactical point of view, one from, okay, is there some very important word that I need to think from that point of view? So it breaks down all those tokens into pieces and then starts processing. It applies the weights, and then each layer is going to generate you something called as key value. All right, so this part that I'm going to talk about is primarily about KV cache. So every layer, it has to go through multiple layers. All of this layers is basically a lot of matrix multiplication, a lot of calculation in terms of division. So all of those operations is happening with the GPU. Okay, you submit some work to the GPU, and the GPU is going to perform. You submit a vector, a matrix, it's going to perform multiplication and give the result to you. So all of those results is in the form of a key value. A key consists of embedding vectors, numerical form, multiplied by some weights. All right, so that is the generator. That is the data that is generated and goes in a loop, right, multiple times, and eventually it starts emitting the first word for the question that you asked, right? And after that, it has to start forming the answer. And for the answer, it moves on to the decode phase. In the decode phase, it starts reusing the vectors, the KV cache values that was generated, and then starts building the answer. So this is pretty standard. All of you would know it, no doubt. So what do we do here? This is a recent work that we did. And KV cache, one of the costliest things with KV cache is you have limited memory in GPU. You need to have GPU memory to be able to save the intermediate states, right? So you have 40 GB on one of the GPUs that we were working on. It can range anywhere from 16 to 94 GB on an NVIDIA system. And on a larger system, you might have more. But then the KV cache that we generate, it can range all the way till 200 GB up to 400 GB also. Depends on the query, the context length. So the context length is another topic that is very useful. If you have limited amount of KV cache, only limited amount of context is what you can support. When you have a, let's say, 32K context, when you have a lot of tokens that you need to parse and come up with an inference, you need to have a lot of memory. So it's not possible to do everything in the GPU memory. You have to offload it onto the system CPU memory, and then from system CPU memory, you can push it down to a storage. Okay, so what does KV cache do? It helps you with this inferencing, supporting longer context. And one of the downsides of this is there's repeated redundant calculation that keeps on happening again and again. So KV cache helps you with saving the context and reusing the context. And larger models can support longer context, and they need lot more storage. Per token, you could have 1 MB to 16 MB of storage needed. All right, so KV cache was launched, and then people moved on to KV cache offload, where they started storing the context in SSD. And then the next stage is, can we store it on a remote storage, right? So VLLM is the inference engine that we worked on, and it has a concept called as paged attention. So where it breaks down a prefix, a query prefix, into pieces called blocks or pages. It is similar to operating system's virtual memory. And this pieces can be saved, and then you need to maintain a life cycle for it, and then you need to bring it into the GPU RAM when necessary to do the computation. So the plain KV cache had a lot of fragmentation problem, memory issues. With the offload, we solved some. But the offload means that, let's say you take a DGX box, it has, let's say, 10 TB of storage. You'll run out of that storage when you have to support a lot more context and a lot more users. So to do that, you have to push it onto a proper enterprise storage, right? So using paged attention, we integrated with page attention to offload the data onto the external storage. All right, so this helps in a lot of shared context, shared information that can be reused. What do we gain out of this? What we gain is, GPUs are a costly resource. You don't want GPUs to be spending so much of time. You can save on power. You can save the cost of the machine. Let's say it's a DGX machine. You can save the cost on it by buying a smaller memory footprint, smaller storage footprint. So you have so much of advantages. So as we begin to build AI, one of the challenges is right now we are burning cash, right? So we'll reach a stage where we have to monetize it. When you start monetizing it, you have to think about how to save, how to provide the same level of convenience to the customer, but then how to save on the cost and make profits. So that's where, that's the angle we look at in Pure Storage. So KV cache is one among them, and we did this experiment on VLLM with a Quen model as well as Llama model, and you can see the difference. The plain VLLM with the Quen model, without a KV cache, it just keeps on going. As the number of context increases, the lower layer is the number of tokens that you use for computing and inference. And as it increases, you can see the response time. So this is basically TFT, time to first token. The first token, so when you enter something into ChatGPT, you'll see analyzing, right? So the first token that comes up, that's the time measurement that we compare with, and you can see that it keeps going without a KV cache. With our KV cache, with our NFS and S3 storage, you can see that it is as good as in memory, as good as GPU memory itself. So we have done a lot of optimizations around it, and with this we can support longer and longer context at a cheaper cost on a cheaper machine as well. All right, so there's another magical technology that is there, which is called as RDMA and associated GDS. You might know DMA and RDMA, some of you. RDMA is basically remote direct memory access, where you treat an external, you talk to two different machines as though it is a local machine. So you talk to an external memory as though it is your local memory. That is RDMA. With GDS is basically GPU direct storage. And what it means is, if you look at a system architecture, if you look at the system architecture, on the left side that you see, it is without a GPU storage. What happens without GPU storage is, when you're working on a DGX kind of a machine, you bring the data into system memory, and then you have to move that system memory content into a GPU memory. So it involves a lot of interference by the system CPU. So with GPU direct storage, you can directly bring the data that is in external storage onto the internal GPU storage and start the inferencing. So GPU technology and RDMA technology is what gets us going, and we have this for the last 2 years in Pure Storage, and it's been yielding really good results to all our customers. So NFS or RDMA technology is the one that we built. We have baseport certification, SuperPod, NCP, which is NVIDIA Cloud Platform. We have all the certifications, and customers are reaping benefits out of it. We have built something new in the last 1 year, which is S3 or RDMA. So if you guys are familiar with AWS S3 protocol, so it is all object-oriented, and you can see the difference that it brings. So when you have a lot of data in S3 storage, typically what happens is you have to bring it into DGX system, where you convert that into a file, and then you feed that file for the GPU, right? So with S3 or RDMA, you can cut short that intermediate layer and directly bring it onto the GPU. So this is the technology that we have, and we have released first part of it. We have almost released, we are going to release it. And this is the underlying technology. I'll skip that out due to time. So the other thing that we do apart from NFS or RDMA and S3 or RDMA is the exascale architecture. These are some existing architecture that is in the market. Okay, I'll skip over it and then take a look at the exascale that we are building. You can go look up the blog around Pure Storage approach to exascale. Sorry. Okay, so what does exascale do? We have a powerful metadata server, which is Pure's FlashBlade. And then we plug in a bunch of data nodes. And here we can achieve speeds like 3 terabytes per second. Okay, I do not know whether you get the thought about what does 3 terabytes per second means, but then it's a huge amount of bandwidth, is a huge amount of throughput that we gain at a very low latency. So these are the ways that we approach AI. As we begin to build AI, keep in mind about how to save the underlying cost. We can't keep going like this in the form of doing a lot more computations. We have to start saving energy, start saving the cost that you spend on the GPU machines. Thank you for listening. Any questions?
Hi, first of all, nice presentation. So I just want to know about, you mentioned about the smart NICs, how it is actually being used, and also if you could actually mention what is the type of smart NIC which you are actually using for the exascale and also for the FlashBlade.
So we use Mellanox ConnectX 7 NICs. Okay. So those are the smart NICs. It supports this offload capability only with RDMA. Okay. So we use that capability. We use Ethernet all around, and we use something called as Rocky, which is RDMA or converged Ethernet. So that enables you to bring the data directly into memory. It doesn't go through the CPU. Directly brings into the memory where you need it. Okay, got it. How about the target side? I understand on the host side. On the target side, is it something like a Bluefield, or if you could elaborate? Yeah, Bluefield, the latest one has ConnectX 7 NIC built into it. Yeah. Okay, thank you. Any other question?
Thank you. Nice presentation. I just had a quick question. So usually people use GPUs because of performance. So throw anything at a GPU, it runs much faster. So with this strategy of KV caching, how are we overcoming some of the performance drops by shifting it to different memory, looking it back up? So just trying to understand the trade-offs that we are having here between using different storage stacks versus directly doing everything on a GPU.
Directly, okay. So you have physical limitation on the GPU in terms of how much memory you have, right? But the models that we use, the GPT-5 that's come latest, GPT-4, for example, that is 1 TB in size in terms of the model itself. More than the model size, the amount of data that it generates in terms of KV cache is also huge. Per conversation, if you have 32K tokens, it can generate 160 GB, 200 GB amount of KV caches. And it keeps on generating this if you want to increase to 128K context, it's even more. So you can't try to put that in a 40 GB VRAM that you have on the GPU. So you have to you have to offload it. And the offload has to be really fast. And you cannot involve CPU to bring the data back to the GPU. You need to have some offloads, and that's where offloads kick in and help you.
Does the offload have any performance impact to the response of the LLM itself is also what I'm trying to get.
Yeah, so we have a hybrid model where we keep what is necessary within the VRAM of the GPU's VRAM, and only when it's like paging, right? So you have your Mac or your system, you have the paging already built in, which is you keep what is important in memory, and then the rest of them is in your SSD or in some other storage. Okay, so you bring in whatever is necessary. So that's the same concept we are extending onto the GPU VRAM, right? And then you offload it. Basically, the paging is what this brings in for GPUs.
Hi, Jayapaul. It was a nice session. I just wanted to check on the cons, whatever you mentioned. You mentioned that there was limitation with respect to VRAM. So can't we leverage the CXL technology to utilize the RAM within the network or over the network to overcome this limitation?
So VRAM is basically just a RAM. It's just a RAM that is allocated for the GPU. And there's physical limitation. So the offload is a capability that can bring the data into VRAM, right? You're talking about the CSI?
CXL technology, Compute Express.
Okay, Compute Express. So let's say whatever is the technology behind it, you have to get it into VRAM for the GPU to work on. It cannot work remotely. We can catch up after the call. Thank you. Thank you.